And this brings us into our theory called plate tectonics.
In March 1980, geologists detected a series of small earthquakes here, beneath Mount St. Helens in Washington state. It was a signal that the long-dormant volcano was waking up. Finally, on the morning of May 18th, it did. Mount St. Helens erupted with a force 500 times the atomic bomb that was dropped on Hiroshima. A cloud of hot ash roared 15 miles into the atmosphere. "230 square miles of forest were wiped out. 6 million trees, enough wood to build 300,000 two-story houses." Throughout recorded history, civilization has lived with the threat of earthquakes and volcanoes. But the cause of their destructive power remained elusive, shrouded in mystery. It wasn't until our first great discovery that a picture of what was happening inside the Earth began to emerge. For centuries, most of what we knew about the Earth's interior came from mining operations like this one. It wasn't until scientists began using seismographs to study earthquakes that they gained a more accurate understanding of the inside of the Earth. When an earthquake occurred, seismographs measured the speed and intensity of seismic waves that vibrated underground. Using this method, scientists identified different layers inside the Earth, each one characterized by changes in rock density. For example, the first layer was the crust, a skin of rock covering the planet. Its depth varied from 3 to 30 miles. Below that was the mantle, with a depth of about 1,800 miles. As for what was below that, a breakthrough discovery provided the first clue. In 1906, British geologist Richard Oldham was analyzing seismograph readings caused by a large earthquake when he saw something odd. As the vibrations from the quake reverberated, they did not arrive at the center of the Earth as expected. It was as if they'd hit an obstacle. Oldham realized the obstacle must be the innermost part of the Earth, a dense mass hard enough to have deflected the seismic waves from going all the way through. Oldham had discovered the Earth's core. It was a landmark discovery because it set the stage for the work of another scientist who was about to help revolutionize our understanding of what was happening inside the Earth. With Oldham's discovery, many believed the picture of the Earth's core was complete. But in the early 1930s, Inge Lehmann wasn't so sure. Lehmann was a Danish seismologist who worked extensively in Denmark and Greenland, studying the velocity of seismic waves from earthquakes. In 1936, she was analyzing the seismic waves from an earthquake that had occurred several years earlier. Seismological stations around the world had made recordings of the same quake. By comparing their readings, Lehmann calculated that as the seismic waves had passed through the Earth's core, there was a change in their velocity, as if they had encountered another boundary of some kind. Then it occurred to her. Something was missing from the accepted structure of the Earth's interior. The Earth didn't just have one core, it had two. The core that Lehmann had found was the Earth's inner core. Today, through precise seismic measurements, we know that it's made of solid iron. Solid because gravity at the center of the Earth creates a pressure 3 million times the pressure it exerts on the surface. The core that Richard Oldham had discovered turned out to be the Earth's outer core. It's made of liquid iron and other elements, a hot churning mass that generates electric currents, which in turn create the magnetic field that protects the Earth from dangerous cosmic radiation. Together, the two cores that Oldham and Lehmann discovered form a massive structure over 4,000 miles in diameter, slightly larger than the planet Mars. At the center of the core, the temperature can be as high as 13,000 degrees Fahrenheit, which is 2,000 degrees hotter than the surface of the sun. To get a better understanding of what we've learned from the discovery of the Earth's two cores, I caught up with Dr. Katherine Johnson, a professor of geophysics doing field research at a mine location in Southern California. What made the Earth hot in the first place?
The Earth's original heat actually came from how the Earth formed. It formed through collisions of smaller bodies, we call them planetesimals. The collision of those bodies released huge amounts of heat that gave
Coming
the Earth
from astronomical distance.
That's right, just crashing into each other and turning all their kinetic energy into heat.
And so that heat's still here.
And that heat is still here. There's also heat that was released actually during the formation of the Earth's core. So all these bodies came together, they're rocky, they have bits of metal in them. That metal settled within the Earth to
Gravity.
Gravity, just by gravity. But the change in its gravitational energy going from near the surface of the Earth to falling to the center actually also released a lot of heat.
Why hasn't the Earth cooled off?
It hasn't cooled off because it actually cools very slowly. That seems perhaps surprising given how hot it is, but its original temperature was very, very hot. And so it takes the Earth is massive, so it takes a long time for it to cool. That's why smaller planets like Mars, even smaller planetary bodies like the Moon, have pretty much cooled off.
But here on Earth, the cooling off of the planet is perhaps billions of years away, thanks to the intense heat of the core, which acts as a kind of natural furnace. What Oldham and Lehman didn't know was what else the furnace was capable of. And that's our next great discovery.